by no means a permanent position because the contract from the heroes gets turned over every 7 years or so, but it's longer than the traditional short-term sort of idea.
You know, I was describing to me the landscape of positions in the UK, and it was so different. It was confusing.
And Oxford in particular is a real mess with that sort of stuff. Oxford have a whole bunch more what we call postdocs. You get a lot of other classes because Oxford tends to attract quite a lot of money from
we've got automatic funding coming through.
Like senior researcher.
I don't understand it myself, to be honest.
It's relatively large.
I think, so I should imagine Hannah will probably become a senior researcher relatively soon.
High flyers
And I'm a step below that. It's just a postdoc.
Weird leap of faith because when they do that, they're not really established.
I think if she wanted to, Hannah could quite easily go and get a lectureship position somewhere in the UK.
The fascinating one is the American system. You get this NIH grant. If successful,
that'd be tenure track, yeah.
You get to extend it.
All right, but then
And then
you
you
don't
get
have
to
to
keep
teach it.
extending.
The same grant.
So they benefit some of the positions.
But are they tenure?
Yeah, so the good
The
thing about
lectureships
These are
are
on
teaching.
grant.
So
yeah,
the
but
tenure track
you have
university, but the grant is with
stability.
the NIH.
So yeah, at some point,
Some people
probably be a
30
relatively
years
good idea
with one
to try and get that, I guess. But
yeah,
it's kind of nice at the early stage to just try and get some research done. And you can kind of do teaching if you want to. So with Oxford, of course, you have the kind of one-on-one tutorial system. But always teaching can be done. Because, you're not giving lectures to hundreds of people. It's like, right, what this student have a teacher? So teaching experience is reasonably okay to come by. So last term I was taking 2 students, I was taking a couple of students. But this term I've got a few more deadlines and things that I'm not going to teach. So it's yeah. I think, but there are positions in Oxford where part of your contract is you have to teach so many hours.
And teaching class.
Yeah. Yes, we have one-on-one tutorials, lectures. Again, not many, probably about 80 people, so it's really pretty small. So I've done a couple of lectures. Just before I left, 20, 30 people. Now it's for applied ethics, which you think be one of the more popular courses. I was a PhD student, so they probably saw my name and the thing, right? I'm going to listen to this guy. But even the ones I went to as a doctoral student, not many people there. So it's not
many. You mean not many
students?
People showing up.
Yeah. Well, I mean, of that cohort, there's a lot showing up. Just Oxford doesn't admit that many people, so you're never going to get hundreds and hundreds of people in a lecture.
Be like
No.
huge giant lecture.
Right. We've had the philosophy faculty lecture hall, 60 people, I think, for a few years. So, when you think about it, how big the Oxford faculty is, a couple of hundred philosophies there, and the lecture field is for 60 people. So,
It's terrible. I still post pictures sometimes.
Illustrates that.
15 years ago.
So where are you?
Only one handy.
Yeah, I'm doing a postdoc. Medical ethics.
I think someday tonight.
Okay, cool. Is there a big grid down there?
There's all divided into medical ethics policy. So I think there's maybe 7,000 full-time faculty.
Oh wow, okay.
4, and then there's
Are you returning?
5 fellows in medical ethics.
So getting an early train back up to Newcastle.
So especially for medical ethics, that's a pretty.
My colleagues
Yeah,
on there.
and it's
Nicola,
great. I really like it there. It's interdisciplinary. So there's psychology,
In the RBI or in
history, legal background.
So he actually is primarily in the brain. He always wanted to be an academic. He was actually the Hammersmith.
Kind of cool. It's
He
kind of what
moved
I
over
hate.
because
I do a lot of
David Brooks
interdisciplinary work.
inspired. So he has to do clinical stuff.
That's pretty well.
And now he's gone back. So he's a PET scanner basically.
Okay.
To your position.
I'm sure he'll run into it.
Yeah.
PET scanning.
Yeah. I don't do so much with pets.
The same all over, right?
At some point, I'm sure you're possible.
Yeah, no,
He's a very nice guy.
But
Very
I,
dedicated.
I'm enjoying my time.
the imaging guys are starting to
Do what I want. I also don't have to teach.
explore
I
territories.
think so. What the difference is,
They've got new pathology
postdocs,
and they're looking at new ways of
fellows usually teach actually.
Is that right? Okay.
So,
It's rare to have a
where are you based?
You're in the center, yeah. I am funded to
almost half of
Spend
the
a lot
time.
of your time in the air.
I'm not a
Europeans.
So what, this is just a stop off to stay warm.
No, it's not. I wish it could be a stop. I have to go back to New York.
I just come back from there actually.
You just came back from New York?
Not
took a picture of you here, so
Yeah,
if you want, I can send it to you.
That's kind of cool that
yeah, yeah.
researched on how to build your.
Yeah, I think part of it
The
is,
CBT of neurotechnology.
maybe I'm wrong about this, but I get the impression that in the UK we have a much more sort of postdoc heavy approach than the US. So my impression is in the US that people do their PhD and then go kind of straight to try and get a tenure track sort of idea if possible.
Yeah, in some fields.
In some, okay. Well, philosophy is
Social science, yeah, philosophy.
whereas in the UK that's, well, maybe it's like 50%, but a lot of people do what I've done, which is get a
Barilan,
postdoc.
Barilan. It's outskirts of
Around
Tel
my
Aviv,
stage,
Barilan.
we go and try and get tenure track.
We have the biggest
I've
brain
not done that
research
because-
center.
Yeah, so if you have that kind of postdoc sort of approach, then
Whom are you collaborate with?
general progression for the
You've
ranks.
been to
so
Israel?
from
I've been to
postdoc,
Israel.
senior researcher. If you stay long enough,
I
you
know a
one
few
of
doctoral
the
professors there.
by bringing in
I
money
know some
or
good
whatever.
ones as well. So I used to
It's
know
kind of
a guy called
recognition
Shai
of, you know,
Shoham.
okay,
He was
we've
a
been doing this for a while, we should probably pay you a bit more than the guy who's just out of
New York,
PhD.
actually.
And they
New York or Yale. I just noticed recently, I saw
Yeah.
the saw
kind
his
of stay
name.
on, like if you're
Yeah.
He wasn't
doing good
happy
stuff.
back in
Exactly.
Israel.
Particularly if you're bringing in grants. So if you've brought in a couple of grants,
So he
then
moved back to the
universities
US. But,
want to try and keep you because
I don't have any
Yeah.
active
That's interesting. Most
collaborators.
people with the US postdocs
I
are
tend,
1 or 2
actually, funny
years.
enough, I've been doing more stuff with other countries in the Middle East, so Jordan and Iraq
Show that you can,
and
the grad
Egypt.
cycle.
Yeah, that's also true in the UK.
Whatever
one year
opportunities
things
come
go.
Sure.
A lot of the time, that will be a postdoc
So I was,
from someone
I was
else's
doing
project who will have had money to
patient
bring
trials
in
in
a couple of postdocs, and
Egypt.
people might have left halfway through the project to
But
get
then
a
I
tenure
had to
track. So
stop
they've still
that.
got a year of
Egyptian
funding
government
left where they need
so
to.
paranoid.
Yeah,
They
right.
didn't like the way we were
They
going
don't-
through
the US
charity groups to
is not
access
at all
these
affected by
patients.
this, say, it's unlikely that
It was
you
a blind
see
community.
higher.
So we're working
Right,
with blind
right.
community representatives to access blind people.
That's usually true.
They
in the
thought
UK.
that this was
I've been, I don't know, I've been pretty
Heroes
unusual. Yeah. Yeah, no, the Hero's got quite a good retention rate in that respect. I think,
So from between you and Hannah, I know that you've been there for.
yeah.
It's funny, what's happening now is we're
Yeah,
getting
yeah. Well, there's this guy, Tom Douglas, who's
a lot
my
of, in the UK
PI,
in
my
general,
previous
we're
guy.
getting
He's
a lot
been
of
there longer
students
than both
coming
of us.
from
He did his PhD in 2008.
Egypt,
He's still there.
Iraq.
Middle East.
But yeah,
But
I think
Egypt, Iraq,
it's
and
one of those
Jordan
as well.
in particular.
During the time, people have come
So
and gone.
Iraq and Jordan, for the
Julian,
last 10
you met
years,
Julian?
we're trying to upgrade their
So he's
academics.
the director
So they,
of that centre. And I think he
so what happens
has
is you get this
kept people he wants to
tenure
keep.
track program in these countries.
One of those has been Tom
They
because
send you out to
he's an
the
excellent
US and
philosopher.
the UK.
He's also got training in
get a
medicine, so he's a fully
PhD.
qualified doctor.
And then you
So
come back with a
having
PhD.
something like that is useful
Only if you get
for
your PhD.
a medical ethics or bioethics
How
centre.
many people are there?
So in terms of
My
permanent,
school has about 120 Iraqi PhD students.
that's 6 or 7 or 8 kind of permanent.
Might not be
Oh, that's what you said. That's the core.
Yeah,
So
yeah,
you're
I very recently joined that. Yeah. As permanent as it gets, anyways.
So it's you, Hannah, Julian, Tom Douglas.
Yep.
Who are the others?
Someone called Guy Gahane, who's done quite a bit in moral psychology.
Okay.
Don Wilkinson.
Okay.
So he's again he's someone who part-time, he's a consultant neonatologist at the
Once all
hospital,
of these people have
but
found
also
things, we'll get started.
does medical.
that's
so again, someone
The organisers asked us just to wait.
Sorry, you're based in Edinburgh.
Yeah, so he's on the main body of people.
I'm not organising it. They just asked me to chair the
at
panel.
the moment it's
So
just
I
that.
have nothing to do with the organisation at all.
There's probably
Which is
another 6
probably
or
why it's
7
all gone so well.
Chancellor's Fellow Edinburgh.
one time.
I
And
was
get,
invited by the
4 or 5
organisers
visitors
as
a
the
term
moderator.
as well. So it's usually.
I know Tom.
Oh great, yeah, he's there in a minute. Yeah, Tom's super nice.
Yeah, he's great. He actually
CGT
emailed me
wasn't up and
yesterday.
running
I
anymore.
totally, because he was actually
No, I think it started
something at Penn.
2000.
Oh, is that right? Okay, yeah.
I don't know if
Okay, good evening everybody and welcome to Brain 2.0, a panel debate at which we are going to explore visions of a neurotechnologically enhanced future. My name's Sarah Chan. I'm a research fellow from the University of Edinburgh with a keen interest in neuroethics, and it's my job tonight to moderate the event. That means I get to do the boring housekeeping announcements at the start. I'm sure it will surprise none of you when I say we have no fire alarms planned, but if there is an alarm, please exit using both doors at the back. Your nearest exit is almost certainly behind you, and the staff will show you where to go. If anybody needs the bathrooms, they are out this door past the lifts on your left on this floor. And finally, we are already in the neurotechnologically enhanced future. I have my neurotechnological enhancement right here with me. I'm sure many of you do as well. Please switch them to silent. Neuroscience and neurotechnology are changing the face of medicine. Technologies such as neurosurgery, deep brain stimulation, implantable devices, brain-machine interfaces, and other forms of neuroscience are revolutionizing the way that we treat conditions such as Parkinson's disease, depression, and other disorders. At the same time, our greater understanding of how the brain works is challenging our ideas about who we are, how we think, and our relationship as well with our bodies. Where is this technology leading us? Are we looking at a future in which we are all somehow cyber enhanced, in which not only do you have your phone in your pocket, but in fact you have your personal connectivity device permanently implanted in your head? Imagine that, no more leaving your phone at home. To help me explore these questions, I'm really pleased tonight to be joined by a panel of experts from across a range of disciplines. So on my right we have Professor Dipankar Nandi from Imperial College. He's a professor of neurosurgery here. And he works particularly on functional neurosurgery with deep brain stimulation and the electrical brain interface. His focus is particularly on the treatment of movement disorders, treatment-resistant depression, and chronic central pain. Next, we have Patrick Degenar. I apologize. Degenar. I'm so sorry. I should have asked you how to pronounce your name. So Patrick is a reader in neuroprosthesis. He's come from Newcastle University, and he is a researcher looking at the use of brain implantable devices particularly for rehabilitative applications. Next we have Meena Taiker. Meena's come to us all the way from New York, so thank you very much for coming to be with us tonight. Meena is the former chief scientist of the Israeli government, and she's a mathematician who specializes in algebraic geometry. Her researching fields include neuro-computation, cryptography, cybersecurity, artificial vision, complex systems, and more. She has served in many prestigious international posts, including the chair of the USA-Israel Binational Science Foundation, and she's been invited to lecture in leading universities and research centres, including, of course, Imperial College tonight. Now on my left, we have Jonathan Pugh. Jonathan's a postdoctoral research fellow in applied moral philosophy at the University of Oxford, and he's currently leading a Wellcome Trust-funded project on the ethics of novel therapeutic applications of deep brain stimulation. His previous research and publications include topics such as the ethics of human embryonic stem cell research, criminal justice, gene editing, and human enhancement. And last but not least, coming to us all the way from the University of Pennsylvania, so thank you, Anna, for making the trip. Anna Wexler is a postdoctoral fellow in the Department of Medical Ethics and Health Policy at UPenn, and her research examines ethical, legal, and social implications of emerging neurotechnology, with a focus on do-it-yourself and direct-to-consumer electrical brain stimulation. Now, the way that tonight's going to work, we would like it very much to be an interactive event, so I'm sure you'll have lots of questions. Do chime in with them. But what I thought we would do is to give us the 101 on the scientific, the technological, the clinical, the ethical, and the social issues. We'll let each of our panellists have a few minutes to take us through the basics. And then I want to bring the audience in for questions. So I know you'll have lots. Do save them up, and we'll open to the audience in due course to have that discussion. But first of all, I'd like to turn to Dipankar and ask, so when we talk about neurosurgery, what sorts of techniques are we actually talking about, and what are these being used for at the moment? What are the potential applications?
Good evening, everyone. I mean, neurosurgery in particular, among all clinical disciplines, actually has immensely changed and gained from technology. Only about 30 years ago, or maybe 40, we didn't have imaging of any decent sort, so it was all very blind, and we did stuff which we didn't understand or could see. I think in the last 30 years, imaging has improved enormously, so we can't see, we still don't understand what we do. About now, I think it's the cusp where our understanding of neural processes and systems, so how the brain kind of gets to do certain things and how it transmits information, maybe a glimpse of how it processes that information. We are getting to grips with it, and very late, we started to use this to modulate work with the brain, because almost all of neurosurgery when I was a resident was ablative. We just hacked out bits and hope for the best. Now, with things like deep brain stimulation, things like prosthesis, you can actually hope to work with existing neural networks and augment function one way or the other. So some things are very common, fairly common now, like cochlear implants, so hearing, where our understanding of certain systems is better than others. So they can do a lot of things and give a lot of useful function. In the particular field of deep brain stimulation, a simple paradigm is where there's movement disorders, so involuntary movements you can't control. So Parkinson's is a common example, tremor. You can hone down to a particular nucleus, small part of the brain, about 3 by 3 millimeters by 3 millimeters, and modulate it. It's still a bit of a black box. We rely on frequency modulated and a bit of amplitude change and see that things are different. A lot of this knowledge comes from animal models, and hence a lot of neurosurgical progress has happened in diseases where there are good animal models. We are slowly hoping to move to artificially created computational models, which should be much more sophisticated, much more relevant to the human system. But yes, these are exciting times, because at long last, without understanding you really can't treat. At long last we have some level of understanding comparable to what used to be for the kidney or the heart 20 years ago. So that's where we are.
Okay, so one of the technologies that's being used quite a bit in this area is implantable devices, yes, to visualize or in some cases to treat. So Patrick, I know you work in this area. I wonder whether you'd be able to outline for us what's the technological future for implantable devices? Where are we now, and where do you think the field is going?
I think the field's very exciting. Like other areas of science and technology, we've got this kind of nonlinear curve that's increasing the amount of understanding and knowledge with time. The field of neural stimulation is very old. The Romans brought neural stimulation to the UK. The Scriptonius Largus, his party trick was to relieve pregnant women by using electric eels, which is the equivalent of TENS devices nowadays. So the field is actually surprisingly old. But really, in terms of modern therapeutics, we can argue that effectively the field started in the 1950s. With the advent of transistors, you could start to develop implantable devices. And the very first heart pacemaker started in 1958. A Swedish guy called Arne Larsson had this first pacemaker fitted, and he had 50 upgrades before he died in the 2000s. And effectively, that's your first generation of devices, which are simple pacemakers. The communication to the nervous system was simply pulse, 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 pulse. It's like banging a drum and hoping the other person understands. The second generation came in the 1970s. So Dipankar mentioned cochlear prosthetics for the deaf. And effectively, if you're to classify these second generations, this is about a one-way communication with the nervous system. This is where you take some information from the outside world, sound in the case of cochlear prosthetics, and then you shout at the nervous system and hope that if you shout hard enough, that the nervous system might understand what it is you're trying to say. And this field is still progressing. Visual prosthetics are still underway. Cochlear prosthetics, people with these cochlear prosthetics, that they can understand speech, but getting music beyond death metal is very, very difficult. Getting visual prosthetics beyond a few flashing dots is exceedingly difficult. There's some interesting clinical trials underway, but to date, the published literature has not achieved more than a few flashing dots in the case of returning vision. But what's really interesting, I think, and this is where we're at the cusp effectively, is this third generation. And this is underpinned by new types of electrical recording and stimulus. It's underpinned by technologies such as optogenetics. But this is where we can start having a conversation with the brain. And by conversation, this means that you're not just taking information and shoving this information directly at the brain in the hope that it will understand, but you actually try to listen to what the brain is saying, and then you modulate your activity based on what the human brain, or animal brain in the case of animal experimentation, is actually saying to you. And a good example of this is perhaps epilepsy. So in the case of epileptic seizures, the brain gets a little bit rowdy. So devices which act like a doorman, which listen into the brain and tell it to quieten down, I think are effectively the first aspect of this next generation. And we already have some devices in play on this, very simple devices. Vagus nerve stimulation, the RNS from NeuroPace, they will effectively listen into the brain, and when it does get too rowdy, they bang a big drum and shout at it and tell it to be quiet. The next generation, which I'm working on, hopes to act more like a noise-cancelling headphone, where when the activity gets beyond a certain area of safety, if you like, you actively try to quieten that activity down. You try to attenuate it. And I think moving forward from this, there's lots of other possibilities. Ultimately, very far down the line, we can think of human augmentation rather than simple medical benefit. Some groups in the US are working on memory. I'd love one of those. But I think for the near future, for the next 10 to 15 years, we're really talking about trying to bring neurological benefit to people with key diseases, things like motor neuron disease, epilepsy, blindness, and auditory disorders. Yeah.
So for people whose nerves don't talk to each other properly, the idea is that we'll be able to help them have that conversation if only we understood what nerves were saying and they understood what we were trying to say to them.
Yes.
So moving on then to Mina, because I know this is a field that you work in, what are some of the challenges then in understanding what nerves have to say in interfacing, if you like, between nerves and brains and machines?
Thank you. I hope that at the end of the evening you'll agree with me that how does the brain work is the most intriguing question for the 21st century. I mean, we have a human brain with 10 to the 10 neurons. Each of them has 10 to the 4 synapses. So together we have a network of 10 to the 14 network that has algorithms that we don't know how they work, that has mathematical rules that we never discovered, that has plasticity that we cannot estimate well, etc. We really don't know much about the brain now. We do not even know how, if you hear the sound ma and you hear the sound mi, somehow in your brain it transformed into the concept of the woman that gave birth to you, mommy. Or if a neuron died on me last night when I had a glass of red wine, how does the function transferred to another neuron? We don't even know, of course we don't know, when a man sees a woman and he decides within a third of a second if she's beautiful or not, how does it work there? And of course we don't know why I like geometry or good in geometry and you are good in algebra. We don't know all that. But we do know a little bit. It's really a little bit compared to what has to be discovered. But with this little bit, we try to do good for humanity. I mean, we duplicate the brain activity, we imitate the brain activity, we interact with the brain, and we cure the brain, as we heard here. When I say duplicate the brain activity, is like artificial intelligence and machine learning or deep learning. We know that the computer plays chess and wins against people. It's vision. It has to do with vision. It's face recognition, and it's also voice recognition and understanding. And when I talk about this is duplicate. When I talk about imitate, I'm talking about decision process, taking decisions. We want to do what the difference between imitating and duplicating, that one is exactly as humans are doing it, and the other one is different. I mean, the machine is doing artificial face recognition different than what we do, but we want to imitate. When we talk about brain-machine interface, the interconnection, we talk about artificial arm that is connected to the premotor cortex. I mean, the place where we decide, not the motor, but where we decide to move the hand, and then activate the artificial hand. And cure is everything that we heard here, and also degenerative, I mean, the epilepsy and Parkinson, degenerative disease, and also neurological disorders. All this, what we are doing, all this, what we are working on, the successful operation, are related to very small groups of neurons that we know where they are, we know their function, and we can activate them. But of course, the future is about the whole system, about total brain activity and thinking machine, in a way that reading the brain and manipulate the brain will be easier for us. And it's very far future, as was said here, even in vision and in other things we are very below, but we want to do it. The problem is that this future reading and manipulating the brain can be also used not to help humanity, as the examples I gave before, but also against humanity. I mean, you can change personality of people, but also create the super bionic soldier. By the way, I heard DARPA is working on that. And also for financial schemes, if you are manipulating one's brain. But this is still far away. And also, another thing that I heard about DARPA is that even though most of what we do are in a small group of neurons, they are working now on a future project that you'll be reading and manipulating 1 million neurons reading and 100,000 neurons manipulating. I want to tell you 4 stories. I don't know if I'll finish the whole 4 stories. Each of them has a question. Each of them has a question that either I answer or will be left for later. One is hypothetical and 3 real stories that connected to me, to myself. Okay, the first one is the issue of an artificial arm connected to your thought. So the hypothetical story is about a teacher that liked to shake the hands in the end of the year in the graduation, and he never could. And when he had an artificial arm, because he was paralyzed, he had an artificial arm, he was happy to do it. But when, in the end of the year, when he was shaking the hands, he was very happy. The last student was a student that all the year was laughing on his disability. So when he shook the hand, the artificial arm kept doing it, kept till her hand was broken. And we know that surgery of the hand is very difficult. Anyhow, her hand was broken. Now the question, whom to blame? Should you blame the programmer, the engineer, the neuroscientist, or the person himself? He was so nervous about this girl, so somehow the neurons next to the premotor cortex were involved and somehow activated his artificial hand longer. So it should be the sign, who should blame for this malfunction? The second story is a work that I did on synchronization and brain activity, some theory on how does the brain work. And we did it with microelectrodes in monkeys. We put microelectrodes in monkeys, 8 microelectrodes that recorded the neurons around them. As I said, a small group of neurons. And then there was a lot of work in order to analyze. And the monkey was taught to make drawings while we did it. And we analyzed the geometry. But I'm a geometer originally, so we analyzed the geometry. Our question was whether to take to this experiment female monkeys or male monkeys. I mean, we couldn't do both monkeys in the experiment because there would be tension in the room. We didn't want this tension, so we had to choose between female and male. And the people that wanted the male, they said there is 1 week a year, a month, that the female monkeys are not operating so well. So we need to have the male. But then we took the female monkeys. You know why we took the female monkeys? Because for the monkey to draw, how would he draw? He gets some juice. Whenever he did something good, he would get some juice. Whenever he did a more complicated, there was a machine that was studying very well if the picture is complicated or no, and then would give him a drop of orange juice into the mouse. So the male monkey was sitting for 1 month like that. He didn't want to draw, he didn't want juice, he didn't want anything. After 1 month, he started to draw. Well, the female monkey, after 3 days, she decided she's not going anywhere, she's there, so she started to draw. So we saved 3 weeks every month for doing that. The third story is about a monkey that was taught to raise his hand. No, it's an original experiment. Before the time that humans were connected to the premotors cortex in order to raise artificial arms, we did it on monkeys. And then there was this monkey that, and at that time, it's 10 years ago, a lot happened in 10 years, there was, the monkey was thinking about, he saw an apple, he was thinking about reaching the apple, but there was a plastic band here that would prevent him from reaching the apple. But he was thinking about reaching the apple, so there was an artificial arm that would go to the apple and give him the apple. So I saw that in San Diego in the big conference, neuroscience conference every year. And I said, what happened? We don't know how to do it. There is no grasping. We don't know grasping. We knew how to locate the neurons of the reaching. So we knew how to do the reaching. But we don't know how the grasping at the end. I mean, to go to the glass but not take the glass. So we didn't know how to go to take the glass. How come they can do it? So, and then I found out that they did it. Actually, the monkey could not grasp it. I mean, the artificial hand couldn't grasp it. Once the hand arrived there, then the monkey, then artificially they would grasp the apple and give it to the monkey, because if the monkey doesn't get the satisfaction of having the apple, he wouldn't collaborate. So actually 10,000 people in the hall thought that there was grasping, but there was no grasping. At the end, also the monkey stopped raising the hand and get hit by the plastic. It was clever enough just to think about grasping the apple, taking the apple, and the apple will come down. The fourth story I'll tell if there's time.
Thank you, Mina. I was enjoying those stories. Fascinating insight into some of the ethical and also the societal issues raised by this research, which brings us very nicely on to Jonathan, who is going to tell us about some of the ethical issues that neurotechnology might raise.
Well, so a few of these have cropped up in the story, so I'll talk a little bit about some separate issues. Drawing what Patrick said, this prospect of cognitive enhancement or human augmentation has really been around for quite some time. We've known for a while that things like diet, exercise, and engagement in general mental activity can have beneficial cognitive effects. So the first question, thinking about this from a philosophical perspective, is, well, are there really any significant moral differences to using these kind of invasive neurotechnologies to augment human performance compared to these more traditional forms of cognitive enhancement? I think there's at least an open question there. But of course, there are some important differences. Right? One is going to be safety. For a lot of these devices and a lot of the drugs that people are currently using as cognitive enhancement interventions, we lack a lot of long-term data about their risk profiles, particularly outside of carefully controlled laboratory experiments. And this is, of course, posing an important question for regulators. What kind of level of risk is it acceptable to expose consumers to? Should we be prioritizing consumer protection by forbidding the use of some of these technologies, or should we be promoting consumer autonomy by letting people make their own minds up about the kind of risk profiles they're willing to buy into of these interventions? But when we're thinking about regulation, we've also got to think beyond the individual risk benefits. We've got to think about societal implications of these technologies. One question that philosophers have been particularly interested in this context is the potential effects that these interventions might have on social justice. One trend of thought has been that if only the rich have access to some of these cognitive enhancement technologies, and they'll simply serve to exacerbate existing inequalities. Now, I think that kind of concern latches onto something of importance, be a little nuanced in how we think about it. I think we need to be careful not to fall into the simplistic assumption that the exacerbation of inequality is somehow built into these technologies. There are important reasons why that might not be the case. One has to do with the technologies themselves. For many of these enhancement devices, we're seeing some evidence that they are in fact less effective in individuals who are already high performing with respect to cognitive ability. So in many ways, they could be used to redress existing disparities in cognitive performance. And more broadly than that, though, maybe the potential to exacerbate inequality just gives us good reasons to regulate the distribution of these kinds of interventions in important ways. So finally, I think the most interesting question really is going to be beyond the questions about equality, and really about the kinds of implications these technologies have for the value of the activities that users are engaged in, and whether they might in fact generate new and important obligations, potentially legal obligations, for individuals to use technologies that are going to enhance their performance in a wide array of different domains. And I think maybe Anna's going to talk about some of the ways in which they're currently being used.
Great, thanks, Johnny. I think you've raised some really important questions there, and I want to focus particularly on what you're saying about risk and regulation and how we give people access to these technologies, or indeed how people are going to seek to access them. So let's say I want that implantable memory chip now, not in 10 or 15 years. Can I go out and get it? Should I be able to go out and get it? So Anna, would you be able to tell us a bit more about the ways in which people are trying to get access to new neurotechnologies and what ethical issues that invokes?
Sure. And so I don't know if the seating on the panel was intentional, but I think on that side, there's scientists and neurosurgeons working on the implantable or possibly implantable state-of-the-art BCI stuff. And Jonathan brought up the word consumer, which is kind of what I study and what my main focus is on. So I'm interested in looking at the set of technologies that are marketed to the general public, so to everyone in the room. You're the target demographic, or the target audience. But these are technologies that are marketed to the general public for cognitive enhancement. And when I think of the consumer neurotechnology landscape, I think it really breaks down into three main categories, at least when we talk about technologies and not drugs or supplements. So first, there's brain training games that have been around for quite a while. I don't know what it's like here, but in the US, if you turn on the radio, you'll hear an advertisement for Lumosity, which is one of the very popular brain training products on the market. It's a software game that claims to improve your cognition, enhance your concentration, that sort of thing. But we're seeing a lot more mobile apps also that are marketed for these sorts of things. So that's one category, right, is the brain training games. The second category, which may be less popular, maybe less of you have heard of, is consumer electroencephalography devices, consumer EEG products. These are basically consumer-grade modifications of research-grade devices that purport to record electrical brain activity and display that activity in some way to you, usually on your phone or through an app. These are sold, again, for cognitive enhancement, often for improving meditation, increasing your focus, reducing your stress, that sort of thing. So that's another class of products. They look like kind of futuristic headbands. The third class is brain stimulation products, which is actually what I've spent quite a few years studying now. And the way these came about is quite interesting. So 10 or 15 years ago, scientists began experimenting with a technology called transcranial direct current stimulation, which delivers very low levels of current to the brain. It sits outside the brain. So at its basic, most crude form, it's essentially a battery with two wires. There's electrodes at the end, and when you put them on your head, your skull, electrical current is thought to flow through the brain. So again, scientists have been studying this in the laboratory, both looking at its uses or potential uses in treatment for a variety of mood disorders and other conditions, but they've also been studying its uses for cognitive enhancement. And in about late 2011, early 2012, I would say, lay individuals began reading about these experiments. deciding that they're pretty easy to make. You know, you can just go out, buy a battery, buy the wires, and construct the devices at home. So the do-it-yourself brain stimulation movement was born around then. So it was about 5, 6 years ago now, maybe a little longer. But actually today it's shifted to more of a direct-to-consumer movement. So there's at least a dozen devices that are on the market right now, marketed to the general public, mostly marketed for cognitive enhancement purposes. Some of them hook right into your iPhone, or you can connect them via Bluetooth and give yourself a jolt of electricity. So some of these are marketed. There's one that's specifically marketed for athletic enhancement. That's called Halo. I'm not endorsing any of these. I have no connection to the companies, I should say. So these are out there on the market now. The regulatory questions, like Jonathan was saying, are very, very interesting. So some of the questions that I think about and that I've written about are how are these devices currently being regulated? Is regulation sufficient? We could talk about this later. I'm not going to go into it now, but you know that because these devices are marketed for enhancement and not medical treatment, they're basically bypassing medical device regulation and sort of, you know, being able to stay on the market without too much issue. But there's real questions about, you know, how should these devices be regulated in the future, and yeah, it's a really big open question, so happy to get into that later.
I'd like actually to gauge the opinion of this side of the panel on that. So let's say I've decided that a bit of deep brain stimulation or something along those lines will perhaps help me think a bit better. Maybe it will mean that my brain's more organized so I can write my papers a bit faster. And I say, well, can I come into your lab and just have a go? Can I give myself a couple of zaps? Is that something that people ought to be able to do, or should I be able to go down the high street and buy one of these electric headbands and use that? Is that going to work? Is it something that should be available on a direct-to-consumer basis? What are some of the issues in relation to that?
I'm not sure. The picture has changed from 100 years, 200 years, 300 years ago, when whatever came was the flavor of the month. Because, you know, when you say, how is it different from marketing anti-aging cream or a six-pack and 6 weeks package or mindfulness yoga business? I think they all, you know, you're marketing something with very thin evidence. It's up to the consumer to wise up and decide what he wants. In terms of danger, I mean, you know, I think the best you can do is regulate guns. They have only one purpose. So in terms of a little bit of, I mean, there's an element of, I take Jonathan's point about individual effect and the social effect. You know, if society picks up the tab of your mistakes, smoking, you know, then there is an issue. But if people want to experiment with a little bit of current, I don't see the problem. They'll soon learn that it may not help.
Great, I'll see you tomorrow afternoon in your lab. Okay, Patrick, did you have anything to add to that from your perspective? Looking
Yes,
into
I think to come back and to emphasize, I think the concept of any brain-enhancing device to normal, healthy human beings is basically quackery for the next 20, 30 years. Yeah, so bear that in mind. However, there are techniques on the horizon which will affect us. I know this discussion's outside the brain, but since this has been raised, I think it's worth mentioning. So one of the key problems in the NHS, in fact health systems around the world, is diabetes. And diabetes is very much type 2 diabetes, to be clear, is very much a self-inflicted disorder. And where it gets really expensive to the likes of the NHS or to any health service is where the individual has been very non-compliant with drugs. Non-compliant, I mean, it's a reversible condition, but it's where the individual has been very non-compliant all the way through to the point where they start getting blindness, legs getting amputated, et cetera, and they start to become very expensive to care for. And as a society, we cannot let them simply drop dead because it's their own fault. So apparently this is consuming now 20% of the health budget. So one of the things that's very attractive and is on the horizon are devices which will simply be implanted and would pretty much overclock the pancreas. Yeah. So these are devices which will listen into the nerve which controls your pancreas, this vagus nerve. You could then overclock this, send additional signals to overdrive this pancreas to work that little bit harder to effectively, prevent or to treat diabetes. And this is very attractive to the likes of the NHS because you could effectively implant this device and let them go for 2 years, and then you wouldn't have to see them again for 2 years. Hence, it could be cheaper. So I think there are some issues about how devices like that could eventually get into the consumer field, especially when we think about all these devices, all these quackery type ideas around weight. But I think for the minute, the idea of brain coming into the consumer domain will not happen in the next 20 years at least. One of the, I would like to, not that will be of any use whatsoever. Yeah. One of the things I would like to pick up on is the ethics that was raised. I think this is a very good point. This issue of social justice. And a very good example that's come into the news lately is an American company called Spark Therapeutics. And they work with gene therapy. And if you think about the next generation of neuroprosthetics, they will mix gene therapies with implants. Now, Spark Therapeutics, they provide a special drug. It's not really a drug, it's a virus that will cure a particular disease. But because it's one-off, yeah, and it's what they call in the US an orphan condition, i.e. it's a minority disease, they're likely only to treat a few hundred people before the patent runs out. And I think it's $300 million have been invested in them. As such, they're going to charge $1 million per treatment. Yeah, and people are assuming this is very greedy. But on the other hand, $300 million has been invested in this particular company, and if the investors don't get their money back, the investment in the field of neuroprosthetics stops. It fails. And of course, one of the other issues that we need to think about, in the end, that $1 million per individual is only for 5 or 6 years until the patent runs out. Yeah, and then once the patents run out, the copycats come in, and that goes from $1 million to $20, $50, whatever, whatever it costs to reproduce these things.
17 years.
$70 maybe.
17 years for the patent.
Yeah, but the patents are usually filed during the research phase. So by the time it gets through the clinical trial, typically, at least in the pharmaceutical domain, there's typically only 3 or 4 years.
Yeah, but you have to be clever not to file all the claims, and then at the end.
No, there's all sorts of tricks and tactics. But typically, you have a limited, you have a limited time. You have a limited time. So, in a sense, yes, you can temporarily increase social inequality, but in the end, you provide the world with a treatment that will be there forever. And that's the advantage of the patent system. Before patents were around, Leonardo da Vinci et al. Used to hide all their best inventions, and the inventions died with them. So yes, the patenting system brings social inequality, but that social inequality is temporary.
I'd like to
say something about this.
Okay, go ahead. Yeah.
In general, I think we cannot stop science. We don't want to stop science. And we just hope that the society will be clever enough to regulate it so the benefits will be more than the disadvantage. So far, we failed in that. I mean, there was an atomic bomb. Everything that we do on the internet, there are so many bad things that are doing against society, against individuals, against government on the internet. Governments are spying on us in a way we don't want to do it. So there are many things that are being handled badly. So that's why we have to be more careful, while not to stop science. As you said, we have to go on. We have to go on, but we have to be careful. In this issue, the damage can be if you change personality of a person, if you make a person a slave and he does what you want when you manipulate his brain, and you don't even to be physically close to him. You can be far away from the person. So the danger is very big, and we have to be very, very careful about it. And it's not enough to do it in every nation by itself. It has to be international efforts to find ways how to prevent misuse, double use of research results.
So the dual use dilemma is one that's well characterised. We can use science for nefarious purposes or for good, and you're right, the question is how do we direct it down the good paths and less of the bad ones. I'd like to ask the ethics side of the panel to comment on some of the issues that have been raised. I'm particularly interested in the story that Mina brought up, the hypothetical about the artificial limb that goes rogue and causes damage. Who's going to be responsible for that? Or what about, so Patrick mentioned implantable devices for blood sugar regulation. And there's an increasing movement now, Anna, you're probably familiar with some of this, for DIY biohacking, where you can get these devices that may be under manufacturer's warranty, etc. But if you want to control a bit more the algorithm for how it dispenses your insulin or reads your blood sugar, you can actually hack into them and change the source code and tailor them to what you want them to do. So what issues does that raise regarding liability? And indeed, what if Mina said that there's the possibility that our brains could be manipulated by other people? What if somebody else hacks your insulin machine or hacks your prosthetic arm? What sorts of concerns does that bring up? Any comments from this side?
Yeah, so well, perhaps I can address the prosthetic story first. I think this is a situation where the ethics needs to be informed by the science in a little more detail, because when we think about moral responsibility in the ethical context, we often talk about it in two dimensions. So we're interested in whether people can foresee the likely effects of a medical intervention, say, and we're also interested to the degree to which they're able to control their behaviour. So in the story you told me, I think what would be interesting when we think about liability and responsibility is first the question, well, is the agent in this case intentionally controlling the hand, or is it really the prosthetic that's kind of taken over some subconscious urge? Are they able to foresee that as a likely possibility when they first consented to undergoing the procedure? Now, if either of those, or both of those are true, if the person themselves knew that this was a likely thing, that the device could take over some subconscious urge and engage in this behaviour that they didn't want, or alternatively, if the person was really exerting control over the prosthesis, then it doesn't seem to me really different in a relevant way to the agent just squeezing the person's hand with their natural arm. So, for me personally, I think here the science is going to inform the ethics a little more. I don't know if you have any.
Anna, any comments?
Yeah, I have so many comments in my head from what everyone was saying. But first, I just want to respond to something that Patrick was saying. So just to the point about all these devices being quackery, I feel like I need to respond to that a little bit. It's a very provocative comment. So 2 points. One, at least from a social science perspective, you know, even if they are, which I'll get to in a second, I'm not sure that they are. Right now, all these devices and products that are out there, it's a multi-billion-dollar market, and so from my perspective, it's there, it exists, and therefore we need to think about how to deal with it. And I think just dismissing it is not gonna, you know, solve anything. You know, you may believe that, but it's not gonna make it go away. And the second issue is, I think it's just a more nuanced question of what's quackery and what's not. So I think the problem with a lot of these devices is there's varying levels of evidence, right? So in the field of brain training, for example, there's good evidence, you know, that if you're, you know, doing one task or training on one task, you're going to perform better in that, you're going to get better at that task, right? But so the question there is the generalizability, right? Does that make you better on other things as well? And so I think there's not consensus. There's debate, certainly, within the research field of cognitive training about how to, what that means, how to define it. There's papers that go back and forth on it. So, when there isn't even consensus within the scientific field, and how are regulators supposed to make decisions about how to regulate something when the science isn't clear? So that's just to say I think it's more complicated than just saying it's quackery. And then the other point I wanted to touch upon was what you brought up about, Sarah, about do-it-yourself medicine, because this is something interesting. So I don't think this is something that's just unique to brain enhancement. So as you mentioned, there's a movement of people who began hacking into their glucose monitors and diabetes devices. It's called it began as something called Night Scout. Now it's called the Open Pancreas Project, where hackers essentially were able to make a closed-loop system which didn't exist on the market until about 5 months ago to automatically deliver their own insulin. But basically, they were frustrated that the pace of medical device development, they didn't feel it was, sufficient. They were frustrated that were carrying around these clunky glucose monitors that did not have any Wi-Fi capabilities. They couldn't monitor their kids' glucose levels, let's say, from afar. So they began to hack into these devices on their own and post the code online. So this is not just happening with brain stimulation. We see this with the Open Pancreas Project. And there's another area that's very interesting, which is DIY fecal transplants. So fecal transplants, those are stool transplants, were being studied as a potential therapy for stomach infections like C. diff, bacterial infections. And they showed very promising evidence in the literature. But again, this was experimental. It hadn't gone through the FDA. But people began reading about it and thinking, we're not going to wait. This is a theme that I think we see coming up again and again, right? People having access to scientific literature, reading about therapies or potential therapies and saying, we're not going to wait. Can we do this at home? So I think these are raising interesting issues, and in contrast to the issues brought up by consumer technology, which is easier to regulate because they're companies actually selling products and you can regulate the company that's selling the product. With DIY, you can't really regulate the individual doing something in their own home. So I think we need to think about new strategies or new solutions, maybe more open engagement approaches to these kind of communities and to these people who are doing these things.
Yep.
I have three brief points, and it's clearly a testament to how interesting Patrick is, that they're all related to what you said. It's just, I agree with Anna completely. It's a very nuanced thing to say, the brain is far too important to believe that people will not experiment with it, play with it, think about it, do stuff, whether it's regulated or not. So I think whether you like it or not, and this is not new. I mean, the longest standing mind enhancer or cognitive enhancer, which has been used by far more people than any pill, has been cannabis, opioids. So people, there's so many of these things. All through centuries they have been there. The other thing is, I envy your sort of decisiveness and certainties in it. Ascribing an ailment to a person's habits or lifestyle is a very slippery slope. And it's, I think, and the third thing is, I don't share this thing about, I have a greater faith in the human spirit. I think most, and if not all of the most important discoveries of mankind far predate the patent system. And even now there's a movement to freeware, open platform, the genetic code. So I'm a great believer that the patent thing is important, but it is by no means a driver of science or new knowledge. So, but yeah.
We could spend a day on patents.
Absolutely.
Only patents for a day.
Can I just raise a little
Yeah,
story?
go ahead.
Just very quickly. It's very good what Dipankar said. So just on this last point, and it's quite fascinating. So I work with an individual called Nick Donaldson in UCL, as professor of neuroprosthetics there. And he interestingly started his life as an apprentice, his working life, under his father, who actually was the, did the original neuroprosthetics in vision back in the 1960s at King's College. And one of the fascinating things he mentioned to me was back in the 1970s, it was brilliant. He used, as a young apprentice, he'd be told by his dad, the boss, that he had to build a certain design because they were going to get it into a patient on the Friday. Yeah. Nowadays, it takes $10 million to $100 million and 10 to 20 years of effort to get into a human being. Yeah. And this is because the regulatory scheme is incredibly tight and incredibly difficult to get around. Now, one of the interesting effects of that then has been exactly what you've been saying, that obviously people with various conditions are feeling very frustrated that these new devices, which, I mean, in terms of a closed-loop insulin pump, there's nothing technically unfeasible about it, but just the process of getting that through all the various trials is so difficult now that we're now seeing these interesting effects that young, talented individuals are experimenting in their own way. And I would feel that, you know, that this is something, you know, if there was a mechanism whereby we were allowed to engage with each other, I think this would be fruitful to the community. How that could happen given university ethics, I'm not entirely sure. But it is something that should have a conversation between, you know, ongoing research groups academically and in business and people who are willing to take that little step further.
So there's a question then, isn't there, about how we ethically manage the risk. We want people to take some risks because that's how innovation goes forward, but at the same time we want to protect people and also insulate manufacturers, I suppose, from liability. So how do we balance those risks out and make sure that we're getting both innovation and safety? And who should decide what's the appropriate level of risk? Is it up to me to say, well, I want to have a go of this, why shouldn't I be able to go out and just try? Or should we be saying, well, actually, no, some things like sticking electrodes in your brain are maybe too dangerous, don't try this at home, kids. I want to actually bring you in on the conversation now. Can I just ask, to gauge a bit of the temperature in the room, how do you feel about the prospect of cognitive enhancement? Let's say if you could go down and get a DIY, let's not do sticking electrodes in your brain, maybe that's a step too far, but if you could, say, try out one of these transcranial magnetic stimulation devices or something like that, who'd be curious to have a go? People in, would you have a go of cognitive enhancement? Sure. Maybe, I think I'd be curious to have a try, but I'd probably want to know that I wouldn't electrocute myself in the process. Okay, so those who are a bit more reserved, what are your concerns? Are you just smart enough already, don't need it, or yeah, do come in. And with questions, if you just raise your hand. I don't think we've got roving mics, but it's a small. We do have roving mics.
Got some behind us.
Oh, great. Well, if you raise your hand, Daria here will bring the mic to you. Thanks, Diana.
Can I respond to something while?
Yeah, go ahead while we get the questions and the mic sorted out.
So in terms of, you know, how do we do this? How might we engage with individuals? So I think there's one really great example so this was a paper that came out 2 years ago, or I guess the summer of 2016. It was authored by 4 neuromodulation researchers, and it was an open letter to the do-it-yourself community. It was actually published in Annals of Neurology and signed by, I think, about 40 other researchers and bioethicists. And what they did was they outlined the risks regarding using this device on yourself at home. And they did it, what was so fascinating about what they did was a lot of the reaction until that point had been, you know, oh, these people are being stupid, they should just stop doing it, right? But rather than saying that or taking that approach, they actually wrote a very measured letter that had a lot of citations and just said, here's what we know, here's what we don't know, these are the risks. And so I thought that was a very interesting and useful example of, you know, a group of professional scientists openly engaging with the community and saying, you know, we're not going to tell you to do it or not do it, but this is what we know and this is what the potential risks are. So that's just one approach.
And this was published in the Annals of Neurology, you
in
said.
2016.
Yeah, I think that there's an interesting question there about how to reach the audiences. In this case, probably they're reading the journals. Another area in which this tension between we want to do it faster and just have a go versus science says, well, hang on, there are risks and you may not be aware of all of them, is regenerative medicine. And I think that's very much a case where simply publishing in scientific journals might not get you the audiences you want. Let's come to the question over here.
Thank you very much. So I understand that it's really would be really interesting, and all the humans have the tendency to want to experiment and see, like, we're curious. So it's good that scientists are able to actually let people know about the risks. But what about the long-term effects of brain stimulation, of TDCS and transcranial electrical stimulation? Are we aware of it, and have there been studies on long-term effects?
Who'd like to answer that?
This is like, sorry.
Yeah, we'll
this is
take
like, the question. French diplomat congratulated Mao Zedong on the success of the Chinese Revolution, 1949, and then he said what do you think of the French Revolution? And he said, it's too early to tell. So if you're waiting for long-term effects, you could wait for, I think in response to what Sarah was saying and what Anna responded, I think the best thing we can do to regulate the level of risk is education. You know, it's like you tell a child, don't touch the fire. Or you rely on as much education which is contemporaneous and which keeps up with the times, knowledge of the time. Because what is ludicrous today, as often history has taught us, is genius for tomorrow. You know, so it's I think, so I just feel it's a almost detrimental angle to go about trying to tell people what to do and what not to do. I think the job of everyone, including scientists and other professionals, is to lay it out in the open and people make their own judgment.
Anna, did you want to comment on this as well?
Yeah. So I think you hit on a very interesting point. And so I have a study that just came out over the holidays that looked at how people use these direct-to-consumer devices and whether they're adhering to the same stimulation parameters that scientists use. And so I found that they mostly adhere to the current level that scientists use and the length of the stimulation session, which is about 20 minutes, but where they depart is in what you brought up exactly, how frequently they're using them. So in studies on cognition, scientists often use maybe 1 or 2 sessions of TDCS. Clinical studies use more, maybe 15, 20, rarely really going above that. It's pretty rare. But I'm trying to remember the exact numbers in my study, but I remember there were 8.4% of respondents had used TDCS 100 or more times. And there was a significant number that had used TDCS, I think 50 plus more times. So they're really using it a lot more than scientists are, and there is no data really on the chronic use of TDCS. So I think that's actually one of the most important issues, and I'm not sure if you're, but you hit right to the point there, I think.
I guess I would point out that we don't know what the long-term effects are of not using it in comparison to using it. So perhaps there's a bit of a bias going on there that we think it's probably going to be bad, or if something bad happens, then we'll feel that we're more responsible because we've intervened in some way.
Yeah, for me, they felt good while it lasted. So, it was a trade-off for everything.
Yeah, great. Can I take a question or comment from over here?
Yes, thank you. So if you look around the room, you can see that everybody is different. And if we think about diseases and treatment with drugs, some people respond really well, some people don't, some people have adverse events. So my question is, how personalized is this new technology going to have to be?
That's a great question.
As much as any current treatment is. So I'm afraid that's exactly the true thing. I mean, you can do the same operation for the same condition on 3 different patients and 3 different outcomes.
Actually, can I jump in here for a second? So the people, I'm a PhD student here, and there are people in my lab who study transcranial magnetic stimulation. And even though it's at this very, very early stage right now, when you combine it with other techniques, for example, EEG imaging and mathematical techniques such as machine learning and Bayesian inference, they're already starting to look at how you can so basically how to use the stimulation given what your brain is doing right now in order to achieve a particular effect. So people are already making inroads in that direction in the basic scientific research.
Thanks, Darren. Mina, you wanted to come in on this one?
Unlike medicine that we take a pill, the culture of taking pills all the time, or other medicine that the study is for the general public, and there is statistics. Let's say it's statistics that 80% it will help you, or 85% it will help you, and with your specification it might be 89 or 80. But the study is general. When someone is doing brain manipulation, it's not a general study that he does. He takes the reading of that brain and manipulate that brain. So it's much more personal than would be than normal medicine today. Maybe in the future there will be more personal medicine. I'm sure there'll be with other things, but when it comes to the brain, it's very personal. That's the answer to your question.
If I may, just very briefly, there is a regulatory issue in this, and this relates to when you put forward for existing therapies and existing neuroprosthetics or even existing drugs, when you put this forward to the regulatory agencies, you have to define its exact operation. You have to define, what are the input parameters in a neuroprosthetic device, for example, sound, what processing will happen, and what will be the output effect. Now, for these first generations of devices, this was very straightforward because, you know, you're just banging a drum. You're just, you know, having a precise beat in the various deep brain stimulations that you work with. You define a frequency, and, you know, that's the way it goes. If, however, you now move towards a situation, these third generation systems, where you're now having a conversation with the brain, and effectively that conversation starts off by learning the language of these local neural circuits, you know, each device is effectively different, and that transfer function becomes different. And that is something that the regulatory agencies do not currently have space for. And it's something that, at least in the projects that I'm working on with, we're actually having to educate the regulatory agencies on how to adapt the rules to cope with these third generation devices. So it's a very interesting question, and it's something that the regulatory agencies are very much behind on.
Okay, a question over here.
So this is probably very hard for me, probably a bit embarrassing. But we know the Army, for example, had internet 30 years earlier than we had, right? And I was thinking, for example, if we had an electroencephalogram and we analyze, for example, we make someone say the word A, the letter A in their mind, and analyze these patterns to see when he's saying A, then we do it with the B and like that. I mean, could we actually, at some point, read the people's thoughts? And I'm saying it's embarrassing because at one point of my life, I was about to enter a Spanish Secret Service, and it was a bit of proven to me that they had these things, then how do you regulate them? First of all, would this way of doing it, is it even possible? That's my answer. Is there a small chance that these things happen, and how do you regulate them if they do?
I'm sure CIA has more weapons and more techniques in their hands than they are advertising. It says that, you know, if there will be a quantum computer, it will change all the world, because quantum computer will break all the codes that are now protecting the banks, protecting the government, protecting everything. It will be like a total cyber attack on everything. So someone said CIA has a quantum computer already, and they just keep it to themselves because it will be a third world war if there'll be. So maybe in that sense, they also have something more advanced when it comes to brain-machine interface or neurotechnologies than we know. But the problem is that, I mean, they have a lot of mathematicians and computer science that could do, and physicists that could do quantum computers silently. But in order to do anything of that, they need a lot of neuroscientists. And the community would know that there's many neuroscientists somewhere that are working. So they could have more than we know. Anyhow, I told you about two things. DARPA is the research and development agency of the American Army. So they're working on bigger population of neurons. They do a lot of things that they do that we are not doing yet. But I don't know if they have the total answer to reading things. Actually, I think they don't have that yet.
Can I just come back to you, if I may? Would it concern you if they can read your thoughts? If anybody could. My point is, you know, where do you hide an apple? In a barrel of apples. People have 1 million thoughts every second. So what do you mean reading your thoughts? Which thought, when? You know, it's such a diffuse target.
Yeah, it's true.
It'll confuse whoever's trying to read your thoughts.
It's probably, I mean, what?
You know, I mean, we think so many things. The human brain is absolutely amazing, and the more we know about it, the more fascinating it is. I don't think there is going to be any algorithm, any kind of computer which will ever, as things stand anyway.
No, eventually, in 100 years. 100 years from now, maybe.
Let me
The
tell
brain
you.
will move on too.
let me come in on this. I've just come back from Washington, where I was reviewing Brain Initiative proposals. So the US have this $1 billion fund called the Brain Initiative, where they're investing in technologies for the brain. The most advanced sort of brain measurement technology at the minute is what's known as optogenetic two-photon microscopy. And this is where, with an EEG or these kind of technologies that you mentioned, these are very coarse devices. I mean, you're very, very limited in terms of measurement of activity. You can kind of understand whether regions of the brain may be lighting up or not, but it would be very difficult to try to determine language or very specific thoughts. So the most advanced method is where you create a window in the skull. You insert a special virus which genetically re-encodes the neural tissue to be light sensitive. And then you use what's known as a two-photon microscope. This inserts infrared light deep into the brain that penetrates a couple of millimeters, typically about 1 millimeter, and then stimulates this fluorescent, reporter that gets presented. And as individual brain cells light up, then you'll see little flashes of light from individual brain cells. And it's possible with this technique to, at the minute, it's about 1 cubic millimeter of the brain that you can monitor every single nerve cell. It's every single activity point in every single nerve cell in the brain. I think the intention is to expand this to about a cubic centimeter, or let's say kind of a square centimeter with a millimeter in depth. So you could measure something like the motor cortex or somatosensory cortex or whatever with this. Could this be used in humans? I mean, this is not a neuroprosthetic. This is a massive microscope, a room-sized system that focuses in on the brain. Could it be used by nefarious agencies? Well, it takes about a month to get this gene expressed, to get this virus working, and there's probably quicker ways that you can get information out of somebody. Using water and a towel. So yeah. But
some places there are readings that they say now the person is thinking of a person or thinking on a car. So to understand if now you're thinking, so the flashlights, as he mentioned, so you can see different readings. And people are very excited for this little advance that we know that this person now thinking of a person or thinking of a car. People are very excited because, as I said at the beginning, we are very, very far from understanding.
Anna, you wanted to comment on this as well?
Yeah, so what everyone's responded there is very interesting. So just two things. One is that you actually people can type out words just using their thoughts now, so they can type out characters using technology that's been around for a while called the brain-computer interface speller. But that doesn't work the way you think it is, so we actually can't read in and say, oh yeah, that's the letter A. But so you know the BCI speller. So yeah, so for people who don't know, so basically that's if you are wearing a research-grade EEG device, not one of these consumer devices, there's a response that typically happens after you see something that you've been keeping in your head. So it's sometimes called the aha wave. So if you're thinking of the letter A, then when you're presented with the letter A, let's say in contrast to other letters, you reliably have this P300 wave. So after a lot of training, and then when you're presented with a series of letters, the speller can kind of figure out which letter you're thinking about. So you can spell. It's very slow and very crude, and you need to do a lot of training. The other thing with thought reading is, if anyone's interested in this, Jack Gallant is doing really interesting work using fMRI to reconstruct images of what people are thinking in their heads. So that's really, really fascinating research that's kind of blows my mind every time I read about it. The lab is doing very cool stuff. But that's not exactly thought reading. Where I think the questions come up is regarding what we can do with AI. And how that may bypass actually understanding. So we may not even need to understand where in the brain you're thinking about A or what a thought is, but if you can capture enough data and correlate it and really have these massive data sets, I don't know, we might be able to bypass the understanding and just be able to translate things.
So we might not know what you're thinking, but we might know what you're going to do next.
I think that's very futuristic, but if it's going to happen, AI, I think it has to.
We've got a question over here.
Yeah, this kind of goes all the way back to what Anna was saying about your study on TCDS and the people who do it on themselves. So kind of linking that to the comment about this stuff being like quackery. So if it's the case that actually people are using this maybe wrongly, but like far further than researchers are allowed to do under ethics, like can we be learning anything from the people who are trying these on themselves? Like, the science have anything to gain from talking to these people, or should we just dismiss it as quackery and, you know, it's not well controlled, blah blah blah? What can we do as scientists?
So it's a really great question, and I actually have a paper that actually addresses the feasibility of doing this. So whether it'd be possible to kind of take the data that people are using anyway and you know, make some sense out of it. So I think in principle, yes, it would be. I think in practice, I think there's so much variability. You know, I don't think the community is that big, and there's so much variability amongst the devices that they're using and what they're using it for and how they're dosing themselves, that I don't think this community is going to be the one where that's going to be that useful. But I think it's certainly an interesting question and should be possible, I think, if there was more people doing it, let's say.
Jonathan?
Yes, I think that's a really important question here. And potentially another strategy for this is to say, well, maybe we need to rethink the way in which we're structuring research and clinical trials. So the technologies we're talking about today, and also all the drugs that people are using, were developed for medical purposes to treat various medical conditions. They weren't created for enhancement purposes. So maybe if people are getting interested in this and using them anyway, we do need to start thinking, well, maybe we should be running clinical trials to test for efficacy for enhancement purposes rather than for the medical purposes for which these interventions were originally created. But that's a way in which would change the whole research framework.
Can I come back on this?
Yeah, sure, go ahead.
You finish up? You want to say something?
I'm going to move on, so please.
I assume you're making the generic point that research at current circumstances, the ethical constraints are sometimes stifling what one can do. I'm completely with you here, because a lot of the innovations which have happened, for example, this is when I was a resident in general surgery, a lot of the operations we do in stomach ulcers. And then one very bright Australian doctor drank a few bacteria and then showed that, so it's all history now. Nobody ever operates on it. Now that would never pass modern ethics. What Patrick was saying, all this investment of millions of dollars to get something from bench to bedside, I think we need to have a good hard look at this. I mean, are we actually stifling creativity, innovation, and future benefit for humankind? Because man, and I use it as a gender-neutral way, is a very curious animal. And trying to curtail that curiosity and a certain amount of risk-taking, I think we do it at our own peril. So I would be very supportive of an environment where properly educated people who know what they're doing are allowed to volunteer for research trials, because otherwise it's absolutely true, but it's absolutely correct. To get to know whether something works or not can take upwards of 3 generations, millions of dollars. It's a futile exercise.
Do you want to come back here?
So I agree to an extent with that. I agree that a lot of research protections perhaps are overzealous and do stuff for research, but they have originally been created for good reasons, right? Because there are well-known historical abuses of research protocols in which third parties have been taken advantage of. So it's quite one thing for a physician to voluntarily take a bacterium themselves, right? It's quite another for them to give it unknowingly to some of their patients to see what happens. So we need to strike a balance here, right? So we need to make sure that we're maintaining the kind of rigorous consent procedures that we have for research. But I agree with you that there is, I think, potentially some way to...
Also the pendulum, is this absolutely religious, fanatic belief in randomized controlled trials. It almost takes leave of common sense. I mean, there's been no randomized controlled trial about shooting yourself in the head, what the result is going to be. And so, half of what I do on a day-to-day basis in my theatres, have never gone beyond level X evidence.
And this comes to some of the previous discussion about how personalised these interventions are, right? The concept of evidence-based medicine for this and placebo-controlled trials and all these things begin to kind of fall away when interventions become this personalised. So again, coming back to the previous question, what's interesting about these technologies is that they may be forcing us to reconsider the whole way in which we consider medical research and potentially enhancing research.
Johnny, you drew an interesting distinction there between the medical uses and the enhancement uses, and I just wanted to perhaps get a different perspective from the panel. So obviously people are quite concerned about coercive uses of neurotechnologies. We're worried about invasion of privacy, infringement of autonomy, etc. And one of the sources we're very concerned about is military. But I wonder whether, given that a lot of the conditions for which these sorts of treatments are being proposed are mental health related, and given the checkered history of psychiatric medicine, are there any concerns around the way that we define disease and what we then offer treatment for? Are we in danger of classifying more and more conditions as diseases now that we have neurotechnologies to treat them? We know that in psychopharmaceuticals, for example, the way that they were developed was actually once we found that we could intervene with the brain, we were able to classify more and more things as diseases in need of a treatment. So now we have a treatment, we can have a diagnosis. Do we think that there's anything to be concerned about there with the shifting definition of disease that these technologies might bring about?
I would wholeheartedly concur. I think we are becoming very intolerant of difference. Everybody has to conform to So children, there are so many now labels for a child who wants to be a bit disruptive or doesn't do what the norm is. 90% of these disorders are fictitious. I mean, they don't exist. And you have now treatments for them, and you have institutes for them. And you ultimately, I completely agree. I think it's taking medicine the other way around. I think the whole point of all this prosthesis work, the stuff which I do, others do, comes from an understanding of the basic neuroscience. I think without that biochemical, organic, imaging basis, or the anatomical basis, it's a very risky path to take behavioral differences among people and class them as diseases.
I agree. For example, ADD or ADHD, now there are many more children that are diagnosed. But I don't think it's because there is a medicine, because the medicine has side effects, people don't like it. I think it's mainly because if you are diagnosed as ADHD or ADD, you get extra hours in school to write tests. So, and you treat it better in school, so the people are coming. I said it's the rich children disease, because only the rich children can go to a psychiatrist or psychologist to be diagnosed with ADD and come back to school.
Yeah, I can just see Anna wants to say something, so let me do that, and then I'm going to take probably one last question. I'm sorry to those who haven't, but Anna, did you want to comment before we move on?
Yeah, I just want to say, so it's interesting that, I think scholars and bioethicists and medical practitioners make that distinction very often between treatment and enhancement. And in some cases it's necessary, right, for regulation. Regulators do too, right? You have to draw a line somewhere between which products or techniques or drugs are considered medical treatments and which are not. So in some sense there's this need to draw these lines. But in another sense, what I've been finding with studying users of TDCS devices is they don't necessarily draw those same lines. So in the study that I most recently did, before asking individuals, have you used it for treatment, we asked them, why did you purchase the device? And they didn't say treatment or enhancement most often. They would talk about the symptoms. So I'm using it to improve my concentration, things like that. But it became difficult. So that was an open-ended question, but it became difficult when we were trying to code their responses. And so our instinct was to code them as enhancement or treatment. But if someone said, I'm using it to improve my concentration, that was one thing, maybe enhancement. But if they said, I'm using it to improve my concentration because I have ADD, would that be considered treatment? So it kind of got blurry. So we found that particularly with diagnosis of ADD and also with regard to depression, there's a kind of cognitive sluggishness that accompanies depression. So if if they said, I'm trying to become more clear-headed because I'm depressed versus, I'm feeling down and I want to become more clear-headed, it was very difficult to code. So I think that we need to question this distinction a bit more, even though I understand why we have to draw those lines.
Yeah, so at a personal level, if something makes your life better, it makes your life better. And whether or not a doctor says, well, you're diseased, you can have this because it's treatment, or you're not diseased, you can't have it because it's enhancement, actually doesn't make a difference to that. If it makes your life better, it's better for you. Yeah, Johnny, did you want to?
Yeah, so very quickly, I absolutely agree with Anna that the treatment enhancement distinction is, you know, a necessary fiction for policy making that doesn't necessarily bear on a philosophical reality, if you like. Yeah, another example of this from the other side is in kind of medicine. You think about vaccination, you could class that as a preventative treatment, but you could also call it an enhancement of the immune system. You know, vaccines aren't a naturally occurring thing. They're something we do to people to boost them. So again, this shows the kind of nebulous boundaries of this distinction. Yeah. Right. Anyway, the point I was going to move on to make is actually coming back to the previous discussion about the definitions of disease in psychiatry. Again, I think this has interesting implications for the neuromodulation context, because when we talk about deep brain stimulation for motor disorders, we have fairly well-defined disease models and a lot of history from animal models. But of course, when we move into psychiatry, the boundaries again become a lot more nebulous. There's a lot of disagreement about how we classify the disease process in things like depression and anorexia. So it's a very exciting time for neuromodulation. We've had great success in the context of motor disorders, but perhaps we still need to tread carefully when thinking about the implications in psychiatry. I don't think we should stop at all. I think there is some very good work being done. But again, there needs to be some reconsideration of how we're drawing these lines and what models of disease we're basing these studies on.
Yeah, completely. That's precisely my point. If you start treating a disease before you even understand it, there is a problem. And that's the thing. Our understanding of psychiatric illnesses or more complex disorders is so poor. I think it's a bit, it's a bit ambitious to try and just stick the electrode somewhere and see what happens. That's what happened in the 1940s.
I was going to say this is what happened in DBS. I mean, you didn't really understand it when you started this process.
That makes that lady's point. Even from those bizarre and barbaric experiments, a lot of knowledge came out, which we now base all our stuff on, and equally human atlases for that matter. So there's a lot of. So I think knowledge as knowledge should be respected, but its antecedents and its, how it came about is a matter for our social justice.
We're nearly at the end of our time. Somebody's been waiting over here very patiently with the microphone. I'm actually going to take, could you ask your question quickly? I'm also going to take the question that I can see up here. And we'll have both of those and then a very quick response from the panel before we wrap up.
Sure. A quick side note, when you're talking about DIY.
I don't think your microphone's working. Could you just speak up a little bit?
Okay. So a quick note about this DIY. There's a difference. You're taking the risk, and when you're researching, you're taking the risk for other people, so it makes your questions. Anyway, that said, my question is more a broad one, bringing it back to the beginning. Don't you think we're jumping too far ahead? Because when you're thinking about like consequences and what can we do, and you're predicting for the next 10, 15 years, maybe you can see where the technology is going. But that is so interconnected with the society and how it interacts with it. So maybe you can have more prediction about the next 10, 15 years. But after that, like, we're jumping so, and in my field of prosthetics, whenever someone thinks of prosthetics, they think like terminating like robots and society. But that's like too far ahead. There's a few generations that will go and people interact with you. There's so many interactions that can you predict.
Okay, so that's one question. Are we jumping too far ahead? And then can I also take the question up the back?
Yes, of course. So in regards to what you were saying about psychiatry and mental health diseases or not, specifically for disorders like ADHD, for example, where in the research there's interesting points or recurrent patterns that we see, for example, a thin prefrontal cortex or problems with norepinephrine and dopamine. I was wondering, yes, these are differences that affect people every day, and should we try to create solutions for that, not only in terms of drugs, because there's so many issues with neurocircuitry and neurochemistry, but also because, unfortunately, BCIs only affect a certain part of the brain, and we can find mental health disorders affecting a different part of the brain simultaneously.
Okay.
Can I respond to that last point? every bit of information we can get about a functioning brain is very important, whether it be from mortal anatomy to current physiological studies. But this last sort of 10 years, there has been absolute dogged faith in PET scans and fMRI. They're probably the two most abused pieces of investigation that you can think of. Anything which lights up. You can change the parameters and make anything light up anywhere in the brain with anything. It is these are like Hawkeye. You're used to the ball falling on the lines. You're not seeing it in real time. It's just a computer simulation of the thing. I think we have to go back. This is lazy science. We have to go back to the basis of how these things work. What is, as I say, you will otherwise completely always repeat these pitfalls because you have a toy and you want to use it somewhere without a knowledge of some working hypothesis. The way old science is to be done. You see something which is odd, you ask a question, you try and answer it. It's slow, it's painstaking, but I guess that's probably the best way you get. So this faith in imaging, which is very, very precocious and it's very mature. PET scans, fMRI scans, they look nice on slides and conferences, but they are it's like the genetic code. We have the whole genetic code, but we have masses of data. In practical applications, still to understand the processes, it's very difficult to translate to the bedside.
I'm actually going to interpret or traduce that the first question a little bit to give each of our panel the chance to have one final say. So I'm often fond of saying that bioethicists aren't fortune tellers. We don't have crystal balls, but we do need, I think, to speculate a bit about what the future might hold for us, where it's going, and how we're going to respond to that. And I think equally scientists need to have a vision about what the future could be to decide whether or not and how to work towards it. So to close, what I'm actually going to ask to each of our panelists is to sum up in one sentence. What's your vision for the world of Brain 2.0? What are you most looking forward to, maybe personally or in your work or for society? What are your hopes? What sorts of things do you think the world of Brain 2.0 will hold for us?
Well, I'm an optimist. I think every 50 years things have got better for most people in the world. I see the same in neurosciences, in my specific field. We learn more, we advance by increments, we do a bit more, and then we learn what we don't know and work on it. But it can only get better.
Bright future. Patrick?
I think it's a long road. It's going to take time, but I can foresee some very exciting devices and therapeutics coming to the fore in the next 10, 20 years. But it will take time. It's not quick.
So don't rush. Mina?
I want to understand how does the brain work and whether some of the models that are now, I want to disprove some of the models that people are using now and come with different models and with the experiment to prove them. Not that I will get a Nobel, but if no experiment to prove it, the model can be fantastic, but it's no good. But in the same time, I would invest my time in order to help medicine. And I do that. I didn't have time to that, but I work on epilepsy from a different point of view. I try to localize the epileptic focus with the mathematical readings of brain activity. And then later it goes to the engineers and the surgeons to work on that. But without total understanding how does the brain work, I will not have satisfaction. And I think it won't happen in my lifetime.
Okay, Jonathan?
I have hopes rather than predictions as a philosopher rather than a scientist, but I hope, based on some evidence, that we will develop safe and effective techniques to treat neurological and psychiatric diseases, which are also reversible. So deep brain stimulation, I think, is a fantastic prospect for that. More broadly, I am hopeful that we're going to have a responsible way, a socially responsible way of regulating technologies that people are and will continue to use, whether we do so or not.
Great, and Anna?
I have to say I'm completely agree with the questioner. So I think things change so much. We don't know what will happen, 10, 20 years from now. So I kind of try to focus my questions in this near-term 5, 10-year period. But I think what I'm most interested in is how DIY and self-experimentation are actually going to change the way that science laboratory science is being done.
So a more public model of science, more collaborative.
Yeah.
Great. Well, that unfortunately brings us to the end of our time. I'd like to first of all thank the organisers of tonight's event. So this panel discussion has been convened by the Centre for Neurotechnology here at Imperial College. And I think I should thank particularly our organisers, Deanna, Dario and Gerald, who are doctoral scholars here at the Centre for Neurotechnology, and also Kate Hudson, who's done an amazing job getting us all here from different places. So thank you very much to these guys for organising and making this happen. And can you all join with me as well in thanking our fantastic panel for a really interesting discussion. Now, I believe that there's a reception afterwards, and I hope that some of the panel will be able to stay around. I'm sorry I wasn't able to get to all of the questions, but there will be an opportunity to nobble them over a drink and ask all of the things you wanted to ask and didn't get to, so please do join us. Oh, sorry.